Hello and welcome everyone to the webinar today. I think we can make a start now. Yeah, my name's Alex Johnson from NanoVision. I'm the Business Development Manager here. And the topic for today is challenges and opportunities for site-specific failure analysis. We're also joined by our invited speaker, Professor Umberto Celano from Arizona State University. And here we go. And yeah, he'll be doing a deep dive into the application area for what he's been working on with AFM-in-SEM for electron beam excited conductivity with AFM. So before we just get started, just to let you know, we do have a Q&A open, so please feel free to add your questions into this area. And we have our experts in the background who will be able to answer these. And then obviously we also have our live Q&A at the end. So beginning with, as I mentioned, I'm from NanoVision. So NanoVision is based in Brno in the Czech Republic. This is the same city as the likes of Thermo Fisher, Tescan, DeLong Instruments. So a wealth of ecosystem within electron microscopy and a really great place to be. NanoVision actually celebrated 10 years last year. And yeah, we are focused on AFM in SEM. This is the AFM product which we have. This is designed specifically for going inside SEM chambers, and the main reason for that is it allows us to combine the benefits of AFM in SEM. As I mentioned, we can combine the benefits of these two different technologies together. So with the AFM focused on modes within topography, using scanning spreading resistance for dopant concentrations, conductivity maps, and IV characteristics for fault finding. And then in addition to that, then within the SEM, we get the fast 2D imaging with the large range of view and being able to do things like surface modifications with PFIBs and looking at elemental compositions. So if we move to the next slide, please. So here we have the setup. It's a fairly straightforward setup. The LiteScope AFM itself connects directly to the SEM chamber, or the SEM stage in the chamber. It is compatible with all manufacturers of SEMs. We just have a small adapter plate with a few screws to mount to the stage. This is really great because it means the system can be taken in and out of the chamber when it's not required, very simply and easily. Typically takes around 10 minutes, depending on the pumping time of the SEM. We then have our nanobox, which is where all the software and control comes from. And we also take the detected signals from the SEM into our software. So this allows us to simultaneously capture information from AFM and SEM in one go. Perfect. Next slide. So this is a really great overview to show the different measurement capability. So if we group it into areas, we have our mechanical properties. This is things like sub-nanometer topography, being able to look at surface roughness, some different other properties, things like hardness, elasticity, stiffnesses. We can then also look at magnetic domain imaging or piezoelectric imaging, and mostly what we'll talk about today is with electrical properties. So things like conductivity mapping, scanning spreading resistance for dopant concentrations, some potential surface mapping as well. And in addition to these, we also have our spectroscopy modes. Okay, next slide. So we cover quite a range of different application areas. Today we are focused more within the semiconductor area, but there are material science, so things like 2D materials, steels, metals, batteries, ceramics, and polymers. also looking at some nanostructures, quantum dots, nanopatterning, nanowires, working with modified surfaces from focused ion beam gas injection systems. And also we work a little bit in the world of life sciences. Next slide. Yes, so here we see the three key strengths, I would say, for why AFM in SEM can be beneficial within the world of semiconductors. So number one is site-specific electrical characterization, and it's really great because you're able to perform localized AFM analysis, things like conductive AFM, scanning, spread, and resistance at a nanoscale precision by navigating directly to specific vias or transistors through the use of the SEM. The second step is being able to merge sample preparation and analysis together. So having a streamlined workflow where you can modify or prepare the sample with inside the SEM. This avoids things like surface oxidation or contamination, and allows for a seamless in situ analysis workflow all within the same vacuum cycle, which is key to getting a high quality conductive AFM image. And in turn, because we're doing everything in a single system or single tool, it means like the workflow is more streamlined for being able to find failure localization, which reduces time consuming things like sample transfers and redundant tools. Next slide. So yeah, we're trusted by many experts within the field. So we have Professor Umberto Celano on today, also Michael Lorenk from onsemi and Libor Strakos from Thermo Fisher Scientific. So we are working with quite a number of people in this field already. Next slide. And now we will focus on some of the workflows that we have developed for site-specific failure analysis. Next slide. A few different working cases. So number one being site-specific PFIB delayering with in situ conductive AFM to analyze NAND structures and for fault finding. Then we have dopant profiling of individual transistors using in situ SSRM. So we can determine between P and N type, and then also we can also quantitatively define the dopant concentrations through the use of a calibrated sample. Next slide. So digging deeper now into the NAND failure analysis. So the challenge is really to be able to understand local conductivity failures by being site-specific. So we developed a workflow utilizing PFIB delayering and in situ conductive AFM, which allows you to do a targeted delayering process to reach and characterize specific vias layer by layer. This allows you to do electrical failures and pinpoint down to individual NAND level utilizing conductive AFM. And all of this is done in a single tool, which means that the in situ sample prep allows us to be fully air-free and prevents surface oxidation, also alleviating some time within as we no longer need to transfer samples from one tool to another. Next slide. And so here we can see the process. So we do the PFIB delayering with the probe moved out of the way, docked away, and then we bring the probe in to do the conductivity mapping. And this can be an iterative process to do layer by layer, all within the same tool. So a seamless workflow. Next slide. So here we see the effects of that. So we have the delayered to get to the different structure, and then the conductivity map. And we can flick through the next slide as well. And then go into the next level. So now we see how the conductivity map is changing layer by layer. And next slide. So for those of you who attended ISFA last year in Pasadena, maybe you saw a presentation from Chuan Zhang from NVIDIA, who showed the work that he'd been doing for site-specific in situ conductivity mapping of SRAM and logic areas on advanced nodes. So here we can see the navigation tool, or using the navigation of the PFIB to direct the AFM tip to the logic areas during the delayering process. And then we also see here the results coming both from logic samples and also SRAM at different layers with the conductivity. It very nicely summed up the benefits of being able to do this. So this streamlined setup allows you to eliminate repeated vacuum cycles. And also, as I mentioned before, maintaining pristine sample surface condition is key to ensuring a high quality conductive AFM imaging. The paper is also free to download, so there is a link there, and we can also share this after the webinar. Next slide, please. So moving on to the next step, we have the MOSFET failure analysis. So this is now focused on dopant concentrations, utilizing in situ SSRM, and allows us to be very site-specific to individual transistors. So this is applicable for things like FinFET and CMOS, and we can already see here the correlation of the dopants with the SEM image in the background. And this allows us to determine between the P&N types at the different parts of the transistor. Next slide, please. If you can flick through it a few times. Yep, that's fine. And so the next step then is also to take it to another level and now quantify the dopants as well. So here we utilized a calibration sample from Infineon with the different dopant concentrations for the P&N types. And then using scanning spreading resistance microscopy, we were able to map these dopant concentrations at a very site-specific area. And then comparing this with some SIMS data, we can see that we get the true quantitative data. Next slide. And an additional workflow that we've been working on has also been to define or measure the doped epitaxial layers thickness. So here we can do it on cross sections, and this allows us to do in situ localized analysis. So there's no need to send samples off to external labs to utilize tools like SIMS or SRP. It can be done directly within inside your SEM chamber. So this allows us to do the mapping directly on your samples and correlate it with the SEM images as well. Without this, it would be near impossible. So this is ideal for things like stacked FinFETs. Okay, next slide. And here we see the results. So we have the SSRM map with the different layer thicknesses. And then also in the profile, we can compare the SIMS data in gray with the SRM data that we collected in red. So we can see that they are following the same patterns, and we can truly say we are getting the correct results. So yeah, thank you very much for that part. That gives you a introduction to AFM in SEM. I'd like to introduce our invited speaker, Professor Umberto Celano, who will do a deep dive into real case situations that he's been using AFM in SEM for, and also the pioneering work he has been doing with the Electron Beam excited conductive AFM. Over to you, Umberto.
Thank you. Thank you, Alex. So just making sure everybody can see my screen and you hear me well. maybe keep an eye on the chat, but I will start like this. Okay, so thank you for the setting up the stage and the introduction, and also, of course, everybody for tuning in. My name is Umberto, and I am a professor with the School of Electrical, Computer, and Energy Engineering at ASU, and my group does a lot of research inside in the space of failure analysis and characterization of material for emerging devices in CMOS. And we are giving a little bit of a different twist here to the ability of using self-sensing AFM combined with electron beams in order to break free from concept of using back contact. Maybe one slide to set the stage. I like this, which is pretty dense, but also helped me to lay out the entire exciting environment where we are currently working. On the left, you get the famous Blackwell introduced somewhere last year using FinFET technologies. You can see the massive size of the chip. I mean, it's as big as the hand of Jensen Huang. These are chips that have been extremely popular for all the incredible success of AI application. On the right, the recently announced, this is not even 3 weeks old, A18 from Intel, Panther Lake. So this one is the first device or first chips which is coming equipped with the gate-all-around. So we're moving away from FinFET and changing architecture into gate-all-around and backside power delivery. Well, it's the first chip from Intel released with gate-all-around. But most importantly, I would say it's the first time that we have a chip which has basically wires on both sides. So if you squeeze your eyes, the front end of the line where all devices are seated, it is somewhere here. On both sides of the chip, you have wires. This is changing dramatically the architecture. It's also changing dramatically our ability to make complex interconnection using advanced packaging solution. And that's the other side of the equation, which is getting very excited. So exciting. Both of these chips are relying on something that people refers to as heterogeneous integration or advanced packaging. There's a lot of jargon there, but the essence is simple. We are dealing with very, very complex system on packages, and they rely on our ability to stack very many dies, in some cases like on the high bandwidth memories that you see here surrounding the GPUs in Blackwell. We are dealing with 12 to 16 dies of memory, which is stacked one on top of the other using microbump technology. There's a lot of bridges, basically some kind of complex type of interposer where we can have redistribution layers, which is connecting different dies from one side to the other. And of course, die-to-die stacking using hybrid bonding is also something which is massively adopted in both these chips. So the reason why I like to show this slide is that on one hand, it shows in essence what are the key metrology challenges that we are facing. So the metrology challenges are here: complex architecture, three-dimensional in nature, a lot of wires and a lot of different materials that are used for the first times in many cases, because actually some of the engineering challenges here had to be overcome with some new solution in terms of architecture and material integration. And finally, never like before, we have this incredible amount of dies and field of view required to be probed. So in other words, it's really for the first time in history, you have to provide a metrology platform that goes from millimeter square down to single-digit nanometer square, possibly in the same tool, possibly at the same time offering correlative metrology solutions. So we do see that as a very exciting opportunity also to do a lot of research. And to some extent, my group does exactly that. So we try to plug in a little bit of the different techniques that are out there and trying to push them to the limits of what can be done to probe logic, memory, new material integration, this kind of stuff. Now, with today, I'd like to guide you through some of these concepts where we use E-beam excited scanning probe techniques. I want to describe how the setup look like, what do we do in reality, and why do we think it's interesting and powerful. And then I want to dive deeper into some real application. And I would say most of this lab to fab keyword or buzzword for many, here I would say it's a fairly let's say, good assessment of what we're doing, because as I want to show you at the end, we think that this is a pathway for making an electrical AFM compatible with some of our inline metrology solutions that exist out there. So This is another busy slide, but I think, again, it can be summarized in one simple statement, which is electrical AFM. It's an absolute staple for the characterization of material, whether you are exploring them and searching for new material properties, and these are some examples, for example, with focus on 2D materials, or if you're using on legacy nodes or on real technologically relevant application, again, whether it's scanning capacitance, whether it's C-AFM on your delayered film, whether it's cross-section SSRM looking for activated doping concentration. So we use a lot of these techniques. We have been doing that for the last 40 years, and it's absolutely fantastic. So the next immediate question might be, if these techniques are so valuable, then when I look into a inline tool, such as this one from Park, you have many other vendors offering inline machines, but the bottom line is none of these modes can be applied inline, or at least literally very small fraction, I would argue practically none of them. And as you know, inline, when we do analysis at wafer scale, mostly it's for morphology. That's really the working horse of AFM. Now, and if you boil down the reason why this is happening, and so what is limiting us, it's a fairly simple problem. And the problem is that most of those techniques I showed you before, they do require back contact. Now, back contact can be of many types, and depending on your sample and situation, sometimes it's as simple as a little droplets of silver paste, sometimes it's as simple as a scratch on the surface, sometimes it's more looking like a little metallic clamp. It doesn't really matter, but you need to have a sort of ohmic contact to collect charges, because these experiments, most of the time, they are based on two probes experiments. So these are like two probes. You apply a bias between tip and sample, and you are capable of collecting tip sample junction properties, whether resistance, capacitance, current, you name it. Okay, so the question that we started investigating a few years ago is like, how do we solve this, and how can we eventually get rid of this back contact and get rid of back contact all at once? And turns out that the self-sensing concept of AFM, it's, in my opinion, a good solution for trying to fix this problem. So on the left, you have the very basic implementation of a normal optically detected system, AFM, so with your 4-quadrant photodiode, your laser reflected on the backside, and of course, your sample plus the incredibly costly back contact, I would argue at this point, since you understand the back contact is limiting me from using this technique in the line. On the right, we have a schematic of the self-sensing AFM operation, in which the key is actually the probe, which is no longer just a passive cantilever, but is somehow an active element constituted of a piezoresistive component. This piezoresistive component is seated in the body itself of the cantilever. It's actually fitting inside a retroactive network, which is based on a wisdom bridge, as a matter of fact. And so by reading out the imbalance of the wisdom bridge, we're capable of understanding what is happening in terms of deflection of this cantilever. Now, you can make the cantilever conductive, like in this case, with some additional platinum coating. So technically speaking, these are conductive probes with self-sensing probing capabilities. And now, Alex explained pretty well and showed a bunch of images. So their system is capable of going into a FIB-SEM, or you can imagine to have this kind of configuration attached to any other existing CD-SEM or any other SEM machine. So there would be some kind of electron beam in place capable of impinging in proximity of your probe. So this is literally the whole idea behind our concept. And so from now on, most of the data I'm going to show are generally acquired in this configuration and in this kind of system where we use self-sensing probe and we use E-beam in proximity of the probe. So the rationale is this. What if I can impinge my E-beam, pump charge into the sample, and therefore get the probe to ground, allowing current to be drained to ground just through the probe, and therefore reversing the usual concept that we do for classic C-AFM. So classic C-AFM would apply a bias in this back contact, provide some sort of voltage drop between tip and sample. And again, the probe is also going to ground, so there would be net flow of charge that goes from your generator into the probe or from the probe to ground. But eventually what you are interested is literally just this charge exchange that is occurring at the tip sample junction. That's what matters. So we started to replace that with this little implementation here. And so in the schematic, we are showing that the SEM is serving us as a sort of voltage generator. So here you need to take that with a pinch of salt. At the end of this talk, I will convince you that this is acting at the same time as a voltage generator or as a current source in some cases. But then for the rest, it's very, very similar to what we used to deal with in a regular system. So we have an intrinsic sheet resistance imposed by the material, which is in between the beam and the probe. Some kind of probe tip sample junction that depends a lot on the material of the probe, depends a lot on the samples you are studying, and of course a little bit of static resistance imposed by the material that you are selecting for your probe, and finally a sort of conductive meter, in this case a sensor that, if we want to implement C-AFM, is nothing else than a transimpedance amplifier measuring linearly the amount of current flowing in the tip sample junction. Okay, so one of the applications that turns out to be almost naturally very, very good fit for this kind of technique, it's literally 2D materials. And on the right side at the bottom, on the right side at the top, I'm re-emphasizing with a better looking picture. What do? We impinge our E-beam next to our probe. There is a 2D material separating the two, and we will scan our probes. This is a self-sensing conductive probe in that area. Now, why is this important? I mean, this is important because most of the work happening on 2D material, it's shown on the left. It's actually occurring on very annoying test vehicle when it comes to applying C-AFM. So it can be as simple as a flake, which somebody might have scotch tape away from a bulkier piece of 2D material and placed on an insulator, in which case the 2D material of interest is isolated from the surrounding. It can be some oriented epi growth or some small wafer epitaxial growth, in which again you will have nucleated islands but not necessarily forming a continuous film. It can be fancier than that if you want to go in the direction of wafer scale, epi transfer, the kind of things where two wafers are placed one on top of each other, and some sort of laser transfer techniques is used to place the 2D material on the from the carrier wafer to the final wafer, or it can be area selected. It doesn't really matter very much. The reality is that you don't want to have you don't have easy time for placing a back contact. In the majority of time, you will have to place something like a FIB deposited metallic line, or maybe more complex than that, or maybe optical lithography. So that's why somehow this was a fantastic case study to start with. And on the right here at the bottom, we do show that independently from our work, it was already 10 years or so that the community has been looking at a different type of application for C-AFM in these materials. And C-AFM does offer a great platform because it allows you to count defect in many senses. You can count individual vacancies. You can look at the edges, grain boundaries, cracks, crystalline defects that occurs in this 2D material, whether they are one more layer or few more layers. Things got also fancier recently with some machine learning and data analysis, which is adding up on the data acquisition itself. So extracting data and information about the quality of your film in an automatic fashion. So we thought this was a great platform. So we decided to test that real quick in a very simple experiment in which the 2D flake here is placed on top of an insulating SiO2 layer. And so we also decided to place a very thick insulating tape between our sample and the chuck. In other words, we wanted to be extremely sure that there was no path for ground through the chuck for our charge. And we went on our flake with the conductive AFM, with the self-sensing conductive AFM, actually measuring nothing in case of beam off, and measured some decent contrast in case the beam was on. So this was just a basic demonstration. Then if I'm pumping charge with an electron beam in proximity in the surrounding here, and this is a fairly large flake, as you can see, so these are still very large images, just proving the opportunity and the possibility to basically inject charge with E-beam inside our probe. So that gave us the ability to say, okay, this is probably something that could work, and we can impinge our beam somewhere and we can perform C-AFM somewhere else. So then we started asking ourselves how small and how close can we get with electron beam impingement. So where do we have our beam landing? This is shown over here. So in this case, we are proving that basically until 10 micrometer away from where you impinge your beam, there is not a substantial difference in the amount of current that you're detecting with C-AFM. So this experiment is done with the probe in point contact, measuring how much current flows in the probe when I'm moving my beam around. Finally, we also start mimicking the ability of the SEM column to inject different amount of current. So this is referring to the beam current of the SEM, and this is referring to how much are we sensing, again, in static point contact, just to prove that to some extent, in this case, for example, you can see there is a very good linearity between the amount of current we are pumping with the electron, with the SEM columns and the amount of current flowing in the tip sample injection, which is an interesting opportunity here because it has the ability to basically tune the signal to noise ratio of your measurements depending on the sheet resistance of the material. We will go back to that in a second, but this is a very interesting knobs because to some extent, and you will see, breaks us free also from some of the existing current limitation when applying a certain bias between tip and sample, because generally you are limited by the amount of volts that your generator can apply, while here, effectively, you are limited by the amount of current that you can pump into the system. And in an SEM, the range is fairly large. Okay, we went over that, and so we look into multiple type of materials. So here it's a very small showcase where we do present a bunch of different type of MOS2, molybdenum disulfide, whether not fully crystallized, whether selected area grown, whether with plasma and CVD, and this is probably more close to a crystalline material, while this one is close to more like an amorphous combination of molybdenum and sulfur. This one is in between, graphene. So in other words, it's just to show you that this is working across different material systems. And on the bottom plots, we show maybe more interestingly, the role of beam acceleration as a function of your current. So once more, we are keeping the distance fixed, and now we are just playing with the beam acceleration. So the amount of energies of the electron impinging the surface. We notice that at some point, I mean, you will start getting a lot of noise, which is energy dependent, so it's really coming up at certain values of your energy for the beam, which in our understanding probably has to do with the fact that at very high energy we generate also a lot of secondary electrons that are almost inevitably getting into our probe. So they get inside, they're launched in our probe, they get into the probe as some kind of parasitic current, and that is messing up our signal to noise ratio. Bear in mind that you very hardly will need to work at this condition, because as a matter of fact, the majority of the experiment I'm going to show you are done with much lower acceleration voltage. So where the noise, it's pretty much the one that you would see and you would have occurring spontaneously. And remember here, this is still like a nanoscience junction sitting on a non-perfect material. There would be minor fluctuation of your tip sample junction resistance, which is impacting also the noise independently from the purity and the quality of your source, I would argue. You can play with the beam angle and somehow the tilt angle between the angle of attack for your beam and the sample. In some cases, we know this can be interesting and it can help us to minimize charging, for example. In other cases, this is not a real issue. As you see over here, no major differences changing with the beam angle and the probe position. Same goes for the distance. Of course, it's somehow important to test working distance, meaning how far is your source from the surface, and somehow what's the impact of that on the final measurements. The selected area growth, it's maybe one of the area where I think this has a more immediate impact and use. So bottom right shows very pioneering work from MIT, where basically the concept of selected area growth came out, or somehow was discussed very much in detail, with the ability of suggesting if we can nucleate to the material just selectively in some dedicated and made on purpose, like some trenches created on purpose with the right surface and crystallinity, then we can improve the quality of the 2D material. And if you think about that, beyond this concept, if we want to use 2D material in any real case application, like growing them for channel purposes in transistors or anything else, it will have to be somehow patterned and selectively grown, much like we're doing today for everything else, source and drain or channels, you name it. And so this is an example. So this is a work in collaboration with our collaborators here at ASU, Setongay and Ivan Sanchez, and of course also sponsored from financially supported by Applied Materials. And so here we show molybdenum disulfide, which is selectively grown in this large area pockets inside aluminum, inside sapphire. So the objective is to go and grow the molybdenum disulfide selectively inside these regions, which are the only one where the molybdenum disulfide will find the right nucleation surface from the sapphire. All the surrounding will have different material, hampering the growth. And actually that works. But then the question is, when you have this isolated 2D material, what do you do to do C-AFM, for example, if you're interested? And in this case, we show you that by just using your E-beam C-AFM, you can recover your ability to study morphology and current for your molybdenum disulfide. Same goes here in a simplified version. This is actually selectively nucleating tungsten diselenide. Not necessarily into this kind of trench, but same goes in here. So these are isolated flakes, and we don't need to apply any sort of wires. We don't need to make any sort of surface back contact or any contamination to the surface. We can just land our probe, land our beam in proximity. I think in both these cases, we're talking about a few tenths of micrometer away. So here you have all those scanning conditions that we use, and we can generate some very, very decent conductive AFM maps for this 2D material. Finally, one interesting work was to prove the use of this in case of 2D material for a very technologically relevant platform. In this case, we teamed up with the CNR in Italy and ST Microelectronics, providing this great sample. So these are somehow 300mm wafers that have been created, patterned, and finally covered all over the places with molybdenum disulfide. Final results, it's something that looks like that. Again, this is a real case in which you don't want to break your wafer when you're dealing with dyes and the material is somehow conformally coating the whole structure that you see over here. These are some sort of SiO2 boxes. If you go at the bottom, you will see our results acquired with a plastic tabletop C-AFM. So in here, we have a back contact. We have to break the wafer. We had to make a back contact with silver paste. And here we're doing the same kind of exercise with self-sensing AFM. Now, although you can probably still see differences between the two and somehow noise levels are not identical, I would argue that if you think that this one here can be implemented with no interaction with the surface, with no destruction of your wafer or no destruction of your die, I would say this is something worthwhile exploring because in my opinion, as I said, it has the pathway to break free from back contact. And also, if you look at the current distribution, you will see that there is nothing really funky between these two measurements. In other words, this is suggesting that most of the differences here are coming from the quality of our amplifier, the quality of our probes in this case, but not necessarily from the physics which is governing the acquisition. So I do believe the physics governing the acquisition is perfectly identical in these two situations. And I think this was actually a very well received paper, and Ashikur, the student working on this project, essentially got the cover of Advanced Science when presenting this data. Now, another community which I think would be very interested is 3,5 compounds. That's again, same story. I mean, this community has a lot of knobs when they're growing their material, and they grow them on wafers already right now, or at least in relatively large area samples, and yet they have to break them and start cutting them in pieces if they want to access this level of details for the information about their quality of the gallium nitride in this case. So here we teamed up with the group of Professor Davidov at NIST, and they have a very, very good facility for growing their own materials, whether in the space of topological insulator or semi-metal semiconductors. They have small Czochralski furnaces, Britian furnaces. So with them, we started playing around with 3,5s, and you see here, these are all E-beam C-AFM experiment. On the left, looking at the reconstructed surface of gallium nitride, in which we can see few actually atomic defects, including terraces. Here we're hitting a sort of resolution which is in the ballpark of 20 to 15 nanometer. Same goes for this image, where we can see screw and mix threading dislocations getting to the surface of gallium nitride. Again, we show side by side for the same material results coming from ECI, which is electron cluster channeling image, where actually we know that this type of defect generally shows up very, very strongly in contrast to basically make sure that we were probing exactly the same things. And all that is done with no back contact, just with our E-beam C-AFM. Here at the bottom, we like to show an interesting case. Again, these two samples that we're comparing, the A and B, they differ in their thickness quite substantially. So the A is very much like 10 times thicker than the B. So we said, okay, if there is any role in the collection of current, the geometrical pathway distancing the beam and the tip, and that is impacting our collection of charge, there must be a trend as I go at a different distance and keep collecting my current, keeping all the rest of condition fixed. This is visible over here. So technically, you can think a little bit about that as a sort of probe-based TLM exercise that we are doing. So transfer length method, in which we are just moving our probe away and we look at the impact of additional sheet resistance kicking in so that we can extract that. In case of identical material, they will show up identical. In case of thickness dependence like this, they will show up the difference in thickness. In case of a difference in sheet resistance, of course, you can pick up the difference in sheet resistance. And of course, in here, we were checking also some of the composition of the sample, because we knew that one of the sample had some silicon doped, silicon doping made on purpose to generate some N-type doping in the gallium nitride. So that's the reason why you also see an XPS next to that image. But the bottom line is, I think for 3.5, it's another kind of success story. Resolution is not really affected. We can hit resolution which is comparable to what do we get with classic C-AFM with back contact. In some cases, as I'm showing over here, this is giving me a pathway for overcoming issues related to the high intrinsic sheet resistance of some of this material, because I can place my electron beam as close as I want, or at least as close a few micrometers as I showed you before, and basically I can pretend that I have a current-induced C-AFM system, so therefore I can pump current also in materials that would have very high intrinsic sheet resistance. One legacy application case for C-AFM, at least historically, has been the qualification of tin oxide, so dielectric degradation. You see this on the left. As a matter of fact, the very first time C-AFM has been introduced, it was to study partially this kind of problem on ultra-thin SiO2 layer. The idea was, can I study the leakage across a very thin SiO2 layer? So we embarked on this work, trying to mimic the same type of experiments. And so that's the most classic implementation you would do for C-AFM. You take a thin film, you scan your probe across the thin film with a certain bias. Literally, it's like having a movable IV characteristics point per point. You generate a map in which dark means there is more leakage than on the bright, and you know what's the leakage distribution. You can use that to study different stages of dielectric degradation. A lot of work has been done in this community for the last 30 years or so. So to do that, in the E-beam C-AFM case, we picked a 20 nanometer crystalline oxide, so titanium oxide, and you can see that after crystallization, this is a material that shows a very strong crystallization, so with the appearance of many grains and grain boundaries, and of course the leakage, which is somehow associated with them. And so when we go down and look at the results with our E-beam C-AFM, now you will realize that we are essentially capable in this case of out-of-plane conduction. So that means that our charges are injected inside the substrate and then collected through the probe point per point across the surface of the titanium oxide. And you know, the most simple demonstration for that is that we would not have any sort of spatial resolution for our contrast if that wasn't the case. So if I would have had any sort of in-plane conduction for my charge, that would definitely not show up like here with the appearance of all your grain boundaries, or the increase in conductivity in proximity of the edges, or the increase of conductivity in proximity of these kind of surface defects in individual crystals. We also did look at these over a few minutes. Actually, these are 4 or 5 scans one after the other to just study how they evolved and what they change. And to a large extent, let's say, we do not observe any sort of crazy transient phenomena or charging effect. So in other words, of course, this is a very preliminary kind of data set, but we suspect that we will be able to generate a lot of the things that traditionally we have been doing on classic C-AFM with back contact, also using E-beam assisted excited E-beam excited C-AFM for thin dielectrics. And I think I want to finish up by mentioning a couple of other things here. I think Alex described the role of failure analysis and site-specific once more. So this is what I was introducing in the beginning. Let's say you now have the issue with your die. You want to have a very large field of view. These are a few millimeter squares you need to open up, maybe using laser ablation. Then you will continue your way down with PFib. And once you do that, now it's time that you should go down and be able to assess feature which are in the single-digit nanometer. So that's exactly what we're showing here for a case of commercial 3D NAND, removing the top layer, delayering down to the area of the pillars, and now at the level of pillars, so we can turn on our E-beam, inject that, and collect our current through the channel. So these are features which are 10 nanometer wide. So this kind of corona that you would see is just 10 nanometer in width, and that can be picked up in this case by using our E-beam. Now, in case of failure, in case of anisotropy, or in case of something you're doing to study the process development, you could probably acquire the whole array of this conductivity for every pillar and try to make some sort of statement with respect to the quality or the intrinsic resistivity or what you're getting from the wire. Remember, there is nothing else here that conducts. I mean, you are injecting your charge in one of the control gate. Hopefully you are hitting your substrate, and finally you are picking up and fishing up your electron through the wire. So inevitably what you will sense in here will be affected by the series resistance of the 3D NAND vertical channel. This is one case where we did that for 3D NAND. Our colleague Chuan just this year did very much the same on logic. So basically delayering, getting access down to the front end, and then using an E-beam to get rid of a back contact and access some of the amount of current that he could recover from different plugs in different position of the front end. Of course, searching for failure, searching for in this case, you need to probably know exactly how your transistors are seated, what kind of well you're expecting. And so you can make a lot of conclusion in terms of the amount of current that you are sensing once you know the architecture that you're studying. Okay, before closing, I want to show this because I think it's an interesting slide. And you might have a lot of questions like we did in terms of the mechanisms and impact of the geometry or charging, for example. This is again the same kind of schematic I showed. Now I want to convince you that if you pick a wire, and in this case it's schematically shown over here, this is an infinitely deep piece of gold, it can be an infinitely deep piece of wire. So we are literally seeing sort of very linear response between our beam current and the C-AFM current. In other words, every electrons we are injecting in, possibly every other electrons that is also secondary generated will be injected in the conduction band and brought somehow down to ground through our probe. And this is offering a few implications I will also discuss later. And then if you do that for thin layers, and these are basically 3 samples that are mimicking 3 different thickness for our layer, 50 nanometer thick gold, 1 nanometer thick molybdenum disulfide, 30 nanometer thick bismuth oxyselenide. The objective is to have just a little bit of a flavor in between thickness for the film thickness and geometry, therefore. So you can imagine this case study, but with the 2D material changing thickness as we go from 1 to 30 to 50. So then we study how is the current evolving in that case as a function of beam acceleration and beam current. Once more, important takeaway is like our beam current is setting up the stage for signal to noise ratio. So in other words, it's not that we cannot work with very small beam current, but simply our signal to noise ratio would not be good enough to generate good looking images. But if we crank that up on top of 1 nanoamp, generally speaking, we are in a safe region where all the samples here we studied could be imaged and could be basically inspected. At 1 keV, as I said before, 1 keV is important. It's a low energy condition, so minimum amount of secondary emitted electron parasitically in your probe, and that's somehow good for the measurement itself. Interestingly enough, you also realize that beam acceleration doesn't matter very much. We hit essentially this saturation regime for amount of current within 5 to 10 keV, which is suggesting that the beam will essentially hit the sample way, way deeper than it matters, especially at this scale. You can do any basic Monte Carlo simulation and realize that at any of these beam acceleration, we will be, impinging and injecting our E-beam very deep compared to the thickness of these layers. So in all of these cases, the relevant amount of charge that will enter the 2D film on the top of the surface, it's already there and it's now contributing for your contrast. So in reality, it doesn't really help you very, very much to work at 30 keV versus 10 if you do not have an objective with respect to that. And finally, some of the beam distance, again, these are massive beam distances from 500 to 100. But again, you can probably just appreciate the fact that even with 500 micrometer distance, using a small amount of beam current, we can get a very distinguishable signal-to-noise ratio, which essentially suggests you can keep the operating condition pretty mild, at least for what it concerns the in-plane transport. Now, we can discuss about what's the impact of the E-beam impinging. There could be, of course, implication there. But what I'm trying to support here is that we are not doing anything crazy to the film itself from the standpoint of injecting in-plane charges, especially if you compare that with our classic operation with conventional C-AFM. And I think two important takeaways are coming out of this slide. So the first is here. This linearity in the presence of metallic sample suggests that we think we can probably implement also some form of E-beam induced STM. Again, STM, especially in the most classic implementation where you limit yourself to doing STM on metals, essentially depends on this ability of you applying your potential on the surface with no sort of hiccups, and therefore we think this is possible. So we're working actively in that direction. We think also SSRM is possible. SSRM, scanning spreading resistance microscopy, does not have anything different compared to this single loop schematic, apart from the fact that your probe must be pushed at very high pressure. That was partially introduced by Alex. And so we think that E-beam SSRM is also obtainable, and we're trying to work in that direction as well. So, and the more work we're doing on the E-beam CFM, essentially, the more we get convinced that most of these 2D or 2 probe contact experiments can be done no matter what. And I will finish here, but I just mentioned that, you don't need to think that this is something very far from the line, because CD-SEM, so using E-beam for CD-SEM, it's something so common. It's a huge market already, projected to grow, because it's literally one of the few things that work in the line when you want to look at small feature. So the idea of adding one self-sensing probe in a machine like this to enable also some sort of electrical AFM all at once in a tool, I don't think it's so far-fetching, and I think it's kind of cool to envision for the future. I want to skip my conclusion because I see my time is running out, and I want to, of course, acknowledge the real doers. So these are the students of the team and the people that are really doing the job in here. So let me acknowledge them, and of course acknowledge also our sponsors and you guys for your attention. I hope there is some questions. I'm happy to take them. Thank you very much.